Great to be here at Q2B. And what I'm hoping to do in the next 20 minutes is to update you on our progress towards fault-tolerant quantum computers. So first, I'm very pleased to share with you a paper that was published in Nature this morning. It shows complex algorithms on 48 logical qubits, not physical qubits, logical qubits. The name of the paper is there, the QR code is there. And what I want to do in this talk is dive a little bit about what it means, what have we shown, and what it means for everyone on the road to fault-tolerant large-scale quantum computers. I would be remiss if I don't start by thanking our collaborators and supporters. None of this work would have been possible without all of these. This work was led by Harvard, performed at Harvard, with participation of QuEra, MIT, NIST, the University of Maryland, and with supports from DARPA, the National Science Foundation, and the US Army Research Lab, amongst others. What are we announcing? We've announced that we have demonstrated using 832 code blocks and implemented a complex sampling circuit. The circuit had 48 logical qubits, 228 logical 2-qubit gates, and 48, you guessed it, logical CCZ gates. We had shown that by increasing the code distance, and I'll describe in a second what code distance is for those that don't remember, by increasing the code distance, we actually get better results. We have shown that we can prepare color code qubits with break-even fidelities, and we've shown fault-tolerant creation of GHZ states, important states in quantum, with 40 color code qubits. So why are we talking about error rate? Why is that a big deal? Well, because if we want to get to where I think everyone wants to get, we need three things. We need a large number of qubits, but even today we see systems with 100 or hundreds of qubits. I mean, our system on Amazon Bracket has 256 qubits, and we recently celebrated its one-year birthday. So 256 qubits have been there for a while. We see systems that are theoretically capable of performing thousands of steps of calculations, but it's the error rate that's killing us. Because if you look at sort of pretty high 2-qubit gate fidelity in physical qubits, let's say 99.6, what 99.6 means that 4 times out of 1,000, the operation will fail. So you're roughly limited to about 250 algorithmic steps before it's basically garbage. So it's really error correction. How do we get beyond 99.6? And it's not to 99.7 or 99.8. What we really want is an error rate of 10 to the minus 13 or 10 to the minus 15. So enter logical qubits. What logical qubits are a collection of physical qubits that encode information in such a way that allows for both error detection and error correction. So as we said, 99.9 or 99.6 or what have you is just not good enough. So logical qubits need to happen to fix that. It's almost like this sort of the quantum equivalent of a classical repetition code. If I wanted to share my credit card number with you, let's say it starts with 416, I could say 444, 111, 666, and then by saying that 3 times, the repetition code, there's a greater chance that if you don't hear me well, you'll be able to recover. And if our environment was truly noisy, maybe I would go and say 44444, or 6 times, or 7, or 9, or 17 times, increasing the chance. So what you see on the screen, the figure on the screen, is one of the figures from the Nature paper, and it shows creation of a GHZ states, which sort of the right side looks pretty standard, but it's the left side. Each one of these triangles is actually a logical qubit. Each one individually is a logical qubit, and then we perform operations on the logical level. Let's just talk about code distance because I mentioned it. A code distance shows how many errors can be corrected. So the formula is if you see a code distance of, say, d, then d minus 1 over 2 is the number of errors that could be corrected. So for instance, a code distance of 3 can correct 1 error, d5 can correct 2 errors, 7 can correct 3 errors. By the way, code distance of 2 can detect an error, not correct one. That still could be useful. And there's a trade-off. I mean, if you go to larger and larger code distances, you require more physical qubits for each logical qubit. So if you have 1,000 physical qubits, then you can start deciding how sensitive is my calculation to errors, and where do I want to sort of set the dial between code distance and the number of logical qubits. So going back to the achievements, 832 code, meaning that we used, it's a code distance of 2 in this particular case, 48 logical qubits, improving the 2-qubit logic gate. We have shown that when you go to code distance of 3 to 5 to 7, then the effect is actually as intended. We are increasing we are decreasing the error rate. We're making it better and better. And so this is a very thick paper, a very complex paper, but with some amazing results. So let me take a step back, tell you a little bit about QuEra and how we got here in terms of what technical blocks had to be in place for the Harvard-led team to be able to deliver these results. So at QuEra, we build and operate neutral atom computers. A year ago, we were sort of glad that we were the first neutral atom computer to launch on a public cloud. You can access it on Amazon Bracket, part of Amazon Direct, or as pay-as-you-go. A year later, we're still the only vendor with a publicly accessible quantum computer. We believe, and obviously we're talking about it here, that we have a clear path to what we consider the holy grail of quantum computing, large-scale fault-tolerant quantum computers. And one of the reasons that we were able to move so fast and make such big progress is our close collaboration and relationship with nearby MIT and Harvard. We're about 50 people based in Boston, and by now, dozens or hundreds of organizations use our product. They publish papers. They have some fantastic results. We have been blessed to be founded by some great scientific minds from Harvard, Misha Lukin and Marcus Greiner, from MIT, Vladan Vuletic, that will give the academic keynote tomorrow, so he can give you more behind the scenes of how this works, as well as Dirk Englund. And this is not sort of the first breakthrough that the joint team has been delivering. We've been doing it all along. We were founded in July of 19. In July of 21, with Harvard, there was a demonstration of 256 qubits. In November last year, we launched that system on Amazon Bracket. In April, the Harvard team demonstrated 99.5 2-qubit fidelity. The 2-qubit fidelity of physical gates is important because if the error rate is too high, then no matter what is it that you're going to do logically, you're not going to be able to overcome the rate in which errors come. So generally, people think that 99% physical 2-qubit gate fidelity is really the error correction threshold. 99.5 is certainly good enough. And today, we're announcing and demonstrating the logical qubits. So in our minds, we are essentially moving from the era of physical qubits, that was lots of fun, to the era of logical qubits, that's going to be even more fun and maybe even more useful. Our quantum computer on Bracket operates today in what's called analog mode. What you see here is a 256 qubits. Each of our qubits is an atom. We can arrange them pretty much arbitrarily. We can move them around. I'll get to that in a second. And in 2024, we're also going to be introducing more traditional gate-based, universal gate-based mode, so you can use it both in the analog mode. That's fantastic for machine learning and optimization, and certainly simulation of quantum effects, as well as the digital mode. And in this past year, we have worked with numerous customers on machine learning applications, on optimization, on simulation. And this experience is going to serve us really well as we get to the next step of doing the same things with logical qubits. So let's talk about the building blocks, what made it possible, what made this, what we feel is a very important announcement possible. The first thing is that we use neutral atoms. So each of our qubits is atoms, and they're what we like to call nature's perfect qubits. Each qubit is identical. There are no manufacturing defects. They're neutral, so they're more resistant to noise. Neutral atom computers operate at room temperature. There's no cryogenic coolers. That both helps with scalability, but it also helps with deployment. When we come to deploy at an HPC center, they're not worried about what are they going to do with the fridge and where is it going to be and so on and so on. And we've demonstrated this high 2-qubit gate fidelity that I just described beyond the error correction threshold. The next important thing is that we can move qubits, and Harvard, with our participation, has demonstrated that we can move qubits while maintaining their state. And that's very, very important, because let's assume, I always wanted to be a qubit. So let's assume I'm a superconducting qubit, and I want to talk with John, who's right there on the back. So if I want to talk with John, I want to entangle with John, and I'm a superconducting qubit, I cannot move. So I have to relay the message to the second row, and then to the third row, and the fourth, and so on and so on. And by the time it gets to John, who knows if the message was corrupted. Now, if I'm a neutral atom qubit, I could just walk over to John. I'm not going to get off stage right now, but I could do that. And so that allows us to create algorithms that are more compact, because we don't have to do all these swaps. It's more error resistance because we don't have to do these swaps. And what you see in this video, and this is a video, it's not an animation. Of course, we've slowed it down so all of us can see it. But you see here that we are moving groups of qubits, in this case, 8 qubits. We move them around. Now, one of the amazing things that allows us to do is what's called a zoned architecture. When you think about a classical computer, like the computer that you may have on your desk, it has I/O, and it has a bunch of registers, and then it has memory. And so what the processor does, it fetches data from memory, it does something with the registers, and then it puts it back. Well, we can do the same things with qubits. And the reason that's important for you on a classical computer is that you can, for instance, double the amount of memory that you have without replacing the CPU. So we are showing in this paper 3 zones: a storage zone where qubits live for a long time. We can shuttle them, we can move them to the entanglement zone, where we can operate on all the qubits that are in that zone, and then a measurement zone that's going to be useful for mid-circuit measurement and error correction and so on. The other advantage is that it gives us fewer control lines. Superconducting qubits, for instance, require about 2 or 3 wires for each qubit. So if you got to 10,000 qubits, you'd need 30,000 wires. That's expensive, that's heavy, that's difficult to cool. It's almost like opening your TV and seeing a wire going to every pixel. That's not so practical. But the Harvard-led experiment showed that we can do all this quote-unquote magic with about 10 controls. And when we scale to thousands of qubits, we may need a few dozen controls, but we don't need thousands of controls. So we truly believe that this is very scalable. The next thing that allows this is related to qubit shuttling is transversal gates. And to do that, I'm going to try to put the remote control in my pocket. And so what is a transversal gate? So let's assume that my hand is a logical qubit, and it's not a really good one. It's got only 5 physical qubits. And let's assume that this other hand is also a logical qubit with 5 physical qubits. And now I want to make a logical qubit operation. Well, what I could do, because of qubit shuttling, I could just move one and overlay it pretty much on top of the other, use a laser beam or electromagnetic field to essentially operate on all the qubits simultaneously, all the physical qubits simultaneously, thereby doing the operation that I need on the logical one. And we've seen, and actually IBM has shown this as well, that with qubit shuttling and qubit movement, you can get more efficient error correction codes relative to having to do a lot of swaps. So the zoned architecture we described, this is a figure from the paper showing the storage zone, the entanglement zone, and the readout zone. And here is, again, this is not an animation, this is a video. This is a video of an algorithm happening, and you can sort of see the caption at the bottom to see what's basically happening. But the storage zone is the one on the bottom. We are doing a whole bunch of operations on qubits. Now we're taking some other qubits, moving them en masse to the entanglement zone, operating on them. And then when we're ready, we're bringing all these qubits together and entangling them as well. So if this looks like science fiction, it looked like science fiction when I started working at QuEra, but it is science and it does work. So where is this going? So one thing, and this is not our work, this is work by the University of Chicago. This is showing these atoms, these individual qubits, are held together in what's called optical tweezers, essentially thin laser beams. This is a photo showing 10,000 individual laser beams. You don't need 10,000 lasers. You take one or more lasers and pass them through a hologram to do that. But this shows that you could theoretically capture 10,000 qubits here. No interconnect required. Everyone can, and this is a small size, room temperature, very flexible. So this is where we're heading, to larger and larger systems. Now, how does one work with QuEra? Well, we can work with you in 3 ways. One is solutions. I mean, people come to us and say, hey, I've got this problem. I want to see it working on your quantum computers. Let's do something together. And we've done several of those. The second one, you can certainly access our computer on Amazon Bracket, but we also offer what's called premium access. And premium access allows you to interact directly with our scientists. And many customers have found that working directly with the scientists really accelerates their program. So you both access our machines, including potentially features that are not yet available on the cloud, as well as interact with our scientists. And then we also sell computers. You know, we can deliver a machine on premises to wherever you are. Now, on January 9th, we're going to have a webinar, and we're going to unveil our roadmap. And I see that the slides are such that even the computer that I was trying to show here is so secret that it went away. Believe me, it's in my PowerPoint deck to begin with. But you can register and see how we're putting that into the field. You can join our webinar and then figure out when will such computers be accessible, how many physical qubits, how many logical qubits, what are we expecting to that. So with that, and I'd like to welcome you to the era of logical qubits. And I think I have a couple minutes perhaps for a question or two.
Thank you, Yuval. Yes, so there are several questions in already. Please, can we have the QR code for additional questions, possibly?
And of course, we have a booth on the trade show, and happy to answer this. Yeah.
Let me go ahead and start off. There's a couple of questions about technical details, such as 2-qubit gate fidelity for the logical qubits and gate speeds. Do you happen to have those numbers off the top of your head? Are they available on the website? Can you talk about that?
So I have about 5 different answers. 1, they're available in the paper. 2, Professor Vuletic will be here tomorrow morning, and he is one of the scientific founders and can help with that. But the point about increasing the code distance is that, yes, you can now increase the gate fidelity. You mentioned speed, and I think it came up in perhaps John Presco's presentation earlier today. No quantum technology is perfect. It does take a little bit of time, microseconds or so, to move these qubits around. However, there are 2 things that we can counter by that. One is that the algorithms are more compact because we don't have to do all these swaps and extra operations to bring qubits together. And the second thing is there are a range of things that we're working on to make the system faster and faster, and make sort of the shot rate, the amount of shots that you can execute at every second, to be higher. Not to mention that with a lot of qubits, you could even parallelize some of the operation.
Okay, thank you. And in the interest of time, let's go ahead and thank Yuval one more time for his talk. Thank you, Yuval.
Thank you very much.